The past of geological engineering. The history of geological engineering stretches back thousands of years, long before it was recognized as a formal scientific discipline. Human societies have always relied on the earth for survival, and in doing so, they unintentionally laid the foundations of what would later become geological engineering. Early civilizations were skilled at observing the natural environment, identifying useful rocks and minerals, and adapting construction techniques to the landscapes in which they lived. In ancient Mesopotamia and Egypt, builders learned to use different stone types for monuments, irrigation systems, and fortifications. The construction of the pyramids required not only architectural vision but also an understanding of rock durability, quarrying methods, and soil stability. Similarly, in the Indus Valley Civilization, cities such as Mohenjo-Daro demonstrated advanced planning, with drainage systems that reflected knowledge of local geology and hydrology. Mining, one of the oldest human activities, was central to the development of geology as a practical science. As early as 4000 BCE, people extracted copper and gold using rudimentary tools. The Bronze Age saw the combination of copper with tin, ushering in an era of metallurgy and resource-based civilizations. The Romans expanded this knowledge further, developing tunnels, aqueducts, and roads that required sophisticated geological insights, especially in identifying safe and stable ground for construction. During the Middle Ages, mining grew into a more systematic practice, particularly in Europe and Asia. The search for silver, gold, and other ores pushed miners to develop early methods of surveying, mapping, and understanding rock formations. One of the key milestones came in the 16th century, when Georgius Agricola, often called the father of mining and geology, wrote De Re Metallica. His work provided detailed observations about rocks, minerals, and mining techniques, laying the groundwork for geology as a scientific discipline. By the 18th and 19th centuries, geological engineering began to emerge as a formal profession. The Industrial Revolution increased the demand for coal, metals, and building materials, requiring deeper knowledge of the earth. Engineers and geologists collaborated to design tunnels, bridges, and railways, often facing challenges such as landslides, ground subsidence, and flooding. This period also witnessed the rise of geological surveys, which helped map resources and create scientific frameworks for exploration. As geology matured into a science, engineering schools began incorporating it into their programs. By the early 20th century, geological engineering became recognized as a specialized field that merged earth sciences with civil and mining engineering. The profession expanded beyond mining into areas such as hydrogeology, petroleum exploration, dam construction, and environmental protection. The past of geological engineering reveals a story of human ingenuity and survival. From ancient builders and miners to modern scientific pioneers, the discipline has always been about understanding the earth in order to use its resources wisely and safely. Its roots lie in practical necessity, but over time it grew into a field that not only serves industry but also safeguards societies against natural hazards and environmental challenges. The present of geological engineering. Today, geological engineering stands as a highly specialized and essential discipline that bridges the natural sciences with practical engineering. Unlike in the past, when it was primarily associated with mining and resource extraction, modern geological engineering encompasses a wide spectrum of applications that directly affect society, industry, and the environment. It has become a field that not only seeks resources but also ensures safety, sustainability, and resilience in human interaction with the earth. In the 21st century, the role of geological engineers has expanded into many industries. They are vital in the search for energy resources such as oil, natural gas, coal, and uranium. With global energy demands constantly increasing, geological engineers apply advanced exploration methods, seismic surveys, and 3D geological modeling to locate and extract resources efficiently. At the same time, the rise of renewable energy has also created new opportunities. For example, geological engineers now evaluate geothermal energy fields and study subsurface conditions for underground carbon storage as part of climate change mitigation strategies. Another crucial aspect of modern geological engineering is infrastructure development. Cities across the world are expanding rapidly, and with them comes the need for tunnels, highways, dams, airports, and skyscrapers. Before any of these projects can begin, geological engineers conduct thorough investigations of soil, rock, and groundwater conditions. Their expertise ensures that construction takes place on stable ground, preventing disasters such as landslides, sinkholes, or foundation failures. Projects like high-speed rail systems, underground metros, and offshore oil platforms would not be possible without their input. Natural hazard assessment has also become a central responsibility of geological engineers. With climate change intensifying the frequency of floods, landslides, and coastal erosion, the profession now plays a leading role in disaster risk management. Engineers study seismic faults to better predict earthquakes, analyze volcanic activity, and design protective systems against tsunamis and landslides. Their knowledge is increasingly used in urban planning, especially in regions prone to natural hazards, where proper geological evaluations can save lives and reduce economic losses. Environmental protection and sustainability represent perhaps the most significant shift in the present practice of geological engineering. Whereas earlier generations focused primarily on resource extraction, today's engineers are equally concerned with minimizing ecological damage and rehabilitating disturbed landscapes. Mine reclamation, groundwater management, soil remediation, and waste disposal projects are standard tasks. Modern engineers work closely with environmental scientists, policy makers, and communities to ensure that development is balanced with environmental stewardship. Technology has revolutionized the profession as well. Remote sensing, satellite imagery, drones, and geographic information systems, GIS, allow engineers to analyze vast areas quickly and with unprecedented accuracy. Advanced computer simulations and artificial intelligence are used to model subsurface conditions, predict landslides, or optimize drilling operations. This technological integration has not only improved efficiency but also reduced risks associated with working in hazardous or inaccessible terrains. Geological engineering today is also deeply international. Large-scale mining projects, oil exploration, and infrastructure development often require teams of professionals from different countries, sharing expertise and technology. Universities now train students with global perspectives, preparing them to work across continents. At the same time, professional organizations and research institutes foster collaboration to address challenges such as climate change, sustainable mining, and renewable energy development. In short, the present of geological engineering is defined by diversity, responsibility, and innovation. The profession has grown beyond its historical roots in mining to become a multidisciplinary science that safeguards communities, supports industries, and contributes to sustainable development. Geological engineers of today are no longer just resource seekers, they are problem solvers, innovators, and guardians of the Earth's systems. Their work directly shapes the safety, prosperity, and resilience of modern civilization. The future of geological engineering. The future of geological engineering promises to be one of rapid transformation, shaped by technological innovation, environmental responsibility, and humanity's evolving relationship with the Earth. As the world faces unprecedented challenges, climate change, population growth, resource scarcity, and natural hazards, geological engineers will play an increasingly central role in securing a safe and sustainable future. In the decades ahead, the demand for clean and renewable energy will redefine the scope of geological engineering. Traditional resource exploration will not disappear, but it will be complemented by new priorities. Engineers will be at the forefront of developing geothermal energy systems, harnessing the heat of the Earth to provide renewable power. Subsurface carbon capture and storage projects will become essential tools in reducing greenhouse gas emissions, requiring precise geological knowledge to ensure that carbon dioxide remains safely contained underground. Additionally, the search for rare earth elements, critical for solar panels, wind turbines, and advanced batteries, will require innovative approaches to exploration and extraction, pushing geological engineering into new frontiers of sustainable mining. Urbanization will also shape the future of the profession. By 2050, nearly 70% of the world's population is expected to live in cities, many of them located in regions vulnerable to earthquakes, floods, or sea level rise. Geological engineers will be tasked with designing resilient cities, where underground infrastructure such as subways, drainage systems, and utility networks can withstand geological hazards. Coastal defense engineering, including seawalls and land reclamation projects, will expand as rising oceans threaten major metropolitan areas. In this way, geological engineers will not only serve as builders but also as protectors of urban civilization. Technological innovation will fundamentally redefine how geological engineers work. Artificial intelligence, machine learning, and big data analysis will allow for highly detailed simulations of the subsurface, making predictions more accurate than ever before. Remote sensing and drone technologies will continue to advance, providing real-time geological mapping in areas too dangerous or remote for human exploration. Advances in robotics may lead to autonomous drilling systems and self-operating underground machinery, reducing risks to human workers. Virtual reality and digital twins of geological structures could allow engineers to walk through underground environments before construction begins, dramatically improving safety and planning. Space exploration is another frontier where geological engineering will find a new role. As humanity looks to establish colonies on the Moon and Mars, geological engineers will be essential in assessing extraterrestrial resources, identifying safe construction sites, and developing methods for extracting water, minerals, and building materials from alien landscapes. Lunar mining and asteroid resource utilization may once have sounded like science fiction, but in the future, geological engineering could become an interplanetary profession. Environmental stewardship will remain at the heart of the discipline's evolution. Future geological engineers will be expected not only to provide solutions for resource development but also to actively restore ecosystems. Large-scale mine reclamation projects, soil and groundwater remediation, and innovative waste management systems will expand in importance. Sustainability will no longer be an optional consideration but a defining principle of the profession. Engineers will increasingly work with ecologists, urban planners, and policy makers to balance human development with the long-term health of the Earth. Education and training for future geological engineers will also change significantly. Interdisciplinary knowledge will become essential, blending geology, engineering, computer science, and environmental studies. Students will need to master advanced software, data analytics, and sustainable design principles alongside traditional geological skills. Professional ethics, particularly regarding environmental protection and community engagement, will be emphasized more strongly than ever before. In essence, the future of geological engineering will be characterized by innovation, adaptation, and responsibility. The profession will move beyond the simple extraction of resources to become a driving force in addressing global challenges. Whether protecting cities from rising seas, ensuring the safety of underground carbon storage, developing renewable energy systems, or exploring the geology of other planets, geological engineers will remain at the center of humanity's quest to thrive in harmony with the Earth, and beyond.